Hello class, welcome back. This tutorial will introduce the NaiveBayes model and how can we build a NaiveBayes model in R. Well, first of all, I will introduce a little bit of the probabilistic model of NaiveBayes, and you will have more detailed explanation in class. So here we just briefly introduce it. So NaiveBayes model is based on this probabilistic model. We want to calculate this posterior probability. So it is the probability of certain level of class of your target variable given the predictor. And it equals to the likelihood. Likelihood is the probability of your predictor given the class level, and also times the class prior probability PC. Well, for example, if your target variable has two levels, yes or no, we can, for example, replace all this C by this yes. So PS equals to the frequency of instances that belongs to class yes divided by all the instances in your training dataset which you use to build this model. And Px is called the predictor prior probability. Well, you can see here, if we change this C, the levels of your target variable from yes to no, this Px doesn't change. So sometimes we skip the calculation of this Px. So after we skip the calculation of Px, we can then transform this posterior probability into this format, assuming that we have n different predictors, and we can, based on this class conditional independence, which we will discuss in class later, we can separate this n different predictors and time them together. Well, now if we now have a new instance coming in, and we want to predict the class level for its target variable, assuming that we have like two levels for its target variable, yes or no. And we will use this formula to calculate the class posterior probability for both class yes and class no using this formula. And then after we have the values of these two probabilities, we then compare their values. For example, if the posterior probability of class yes is larger than class no, we'll predict the class level for its target variable as yes, while otherwise we'll predict as no. Next, we will demonstrate in our Markdown file how can we build a NaiveBayes model in R. And first of all, we will use a new dataset called car auction dataset. Let me first import this dataset into my R. And here we want all the character variables as factors. So we set the strings as factors parameter equals to true. And let me see the structure of our dataset. So as you can see, in total we have 10,000 observations and we have 11 variables. While we have our target variable is byte by, and the rest 10 variables are predictors. So in total we have 5 different factor variables, and the rest 5 are integer variable, numeric variables. Well, you can also use the summary function to have a little bit statistic results for numeric variables and also the frequency for the factor variables. Well, we will not do any exploratory analysis here, but if you're interested, you can do that offline. So one thing we want to check is the distribution of the target variable. So let me use the table function to generate the frequency just for the is byte by variable. So you can see here, we have a lot more instances belongs to the class no, and we call this dataset imbalance. Well, it means that the number of instances belong to one class is larger than the other classes. For example, here the instance in belongs to class no is 8 times the number of instances belongs to class yes. And we also can call it, besides imbalance, we can also call it skewed. And next, in order to build a NaiveBayes model, we need to partition our dataset into training and testing dataset. So we need at least one training and one testing to build the model and then to test the performance, to evaluate the performance of this model. So still, we are gonna to load this package current, and then well, remember to set seeds in order to get the same random sampling result each time you run this R command codes. So we will use 500. This 500 we just random select this seed number. Well, we will still use this create data partition function which we used before in other tutorials. And here we set this p equals to 0.67, which means we want the 67% of the instances goes into the training dataset, and the rest of 33% of the instance goes to the testing dataset. So this create data partition function will generate a set of the randomly select row index. So we use those index to build our training dataset, and then the rest of the rows to build our testing dataset. Well, in order to check if we have we did randomly select our samples, we will first check the rows of both of our training and testing dataset. Let me run both of lines. So basically, because we have 10,000 different observations, and basically 67% of them goes to the training, and the 33% goes to the testing dataset. Well, let's see if we did randomly select both of our datasets. Well, as you can see, the probability distribution of our target variable is bad by for both of our datasets are similar. So basically, we did a great job using the create data partition function. Well, after all this preparation, now we need to build this NaiveBayes model in R. Well, we will use this package called E10.11.71 package to create our NaiveBayes model. Let me first load this package and then load the R minor package. Well, similar to the decision tree classification models, well, similar to the C5.0 and J48, this function called NaiveBayes, and you can directly use this function to build our model. So the first parameter looks similar to the parameter we did with the decision tree. The first parameter looks like a regression model. So our target variable is bad by, and then the dot represent all the predictors besides our target variable. So we want to use the rest 10 variables as predictor to build a model to predict the target variable is bad by. And remember to only use the training dataset to build this model instead of the whole dataset or the testing dataset. So let's build this model together. Well, next part is very important. We want to check the summary of this model and how can we interpret this model. Well, you can check the summary of this NaiveBayes model by calling its name. So let's call its name and see the summary. So let's check it from top. So in order to calculate the posterior probability of each class level of the target variable, we need first the likelihood, which is the probability of predictor given the class level. And we also want the class prior probability. So here we have a lot of tables with probabilities and also numbers. So this table, no and yes, the probabilities are the class prior probabilities. So the P yes equals to 0.1295 and the P no equals to 0.87046. Well, next we will see the conditional probability tables. So for each categorical factor variable, for example, this auction, the likelihood, which is the probability of this predictor given the class level, we can check from this table. For example, I want to see the P, the auction value Adisa given class no. Well, this likelihood, this probability equals to 0.1897823. Well, similarly, next factor variable color, well, given the likelihood, which is a P black given class yes, equals to this 0.091013. So basically, for each factor variables, NaiveBayes model will present you the conditional probability table, which are the likelihood you need for to calculate the posterior probability. So these probabilities are generated based on the training data set. Well, if we have a numeric variable, for example, we have 5 integer variables which are numeric. NaiveBayes model could not calculate their frequency and also their probabilities. Well, they will calculate the average and the standard deviation. For example, here we have a numeric variable, average price, and NaiveBayes will present you, okay, the average price for of instances that belongs to class no, and the standard deviation for the average price that belongs to the class no, and so on. Well, this is the average price of this variable, average price, that belongs to class yes, and also this is the standard deviation. Let's see. Well, you can calculate these probabilities, conditional probabilities, one by one using the prop.table functions. So let's use this prop table, and we use the margin equals to 2. So let's see. So you can see this is the probabilities we get from this auction using the prop.table function, and this is the probability table generated by the NaiveBayes model. So these two, the values inside these two tables are the same. Well, sometimes we may ask you to calculate these conditional probabilities by yourself manually. So how can you calculate this probabilities with only the frequency table? So here we will briefly show you. Let me get the frequency of the categorical variable auction, for example. So now I have a frequency table of auction with the three levels of values given the class level and no and yes. So let's see. So now we have this frequency table. So the 1107 is a frequency that belongs to the number of instances that belongs to a DISA and also belongs to class level no. So in order to calculate this posterior probability class no given predictor DISA, we need first calculate likelihood, the P, DISA given no, and also the class prior probability P no, and the P DISA, which is predictor prior probability. Let's first look at this likelihood. So the P DISA given class level no equals to this 1107 divided by all the number of instances that belongs to class level no. So we sum these three values as denominator, and this value equals to the result that we saw in the NaiveBayes model summary. And next, we will calculate the prior class probability P no equals to the number of instances that belongs to class no divided by all the instances that you have in your training data set. So this value also is correct. And the next one is skippable. So the P DISA is the DISA predictor prior probability equals to the numbers of instances that had this value DISA, which is this sum of these two values, and divided by all the instances, number of all the instances in your training data set. So now we can calculate the posterior probability P class level no given predictor DISA. It equals to this likelihood times this class prior probability divided by this predictor prior probability. Well, in terms of numeric variable, here we will briefly introduce two approaches we can use to calculate the likelihood, for example, the P predictor given class level. So we have one numeric variable called odometer. So here, NaiveBayes model will calculate their mean and standard deviation values given class level no and yes. So we want to have this likelihood, the P, the probability of odometer given class level no or class level yes. We will use this function. This function is the probability density function for Gaussian distribution. And if you want to calculate the likelihood of odometer given class level no, you just substitute the mu and sigma with the mean and standard deviation values given class level no. The next approach we can use is simply convert this numeric variable into a categorical factor variable. For example, this method is called binning method. So you have to search for this split point. So between each splitting point, there is a bin. So the values that fall into these bins will belong to one level for this categorical variable. After checking the NaiveBayes model, the next step is to make some prediction on the test dataset. We will still use a predict function, and the first parameter is the NaiveBayes model name, and the second parameter is the test dataset we have, and this will generate a set of predictions just for the target variable for each row in the data in the test dataset. So let's check the first top 5 predictions for the first top rows in the testing dataset. So basically, this model predicts the first top rows instances as class no. And next, we will evaluate this NaiveBayes model using the confusion matrix. We will use a print function just print out the results. So let's see. We can check our confusion matrix here. Well, because we have a very imbalanced dataset, very skewed dataset, while the number of instances inside belongs to class level no, is bigger than the number that belongs to class level yes. So you can see that we correctly classified 2,723 instances into class level no, but we only correctly classified 124 instances into class level yes. We made a lot of mistake in misclassifying the 303 instances into class level no, but actually they belongs to class level yes. So that's why the accuracy looks relatively good, but the sensitivity for our positive class level yes, is low. Well, you can also use the metric function that from the RMinded package to calculate accuracy, precision recall, and F measures. So let's run this function. So you can see here we have the precision recall F measure for both class levels. So you can see the precision and recall for class class level yes is relatively low because yes is the minority class. Minority class is the class that has less instances than the other class. Well, so basically that is everything we will cover in this tutorial, and thank you for listening and thank you for your time.